Alrighty, let's take a look on page 181. We're going to start our next section today, continuing to look at x-intercepts. We're going to kind of slide away from positive x-intercepts, negative x-intercepts, zero x-intercepts, imaginary x-intercepts, just for this section. And we're going to talk about how we can figure out where some x-intercepts are located a little bit more specifically. So maybe we do have a positive x-intercept, but where is it located exactly? Now, I know we've also talked about how we can figure out where x-intercepts are by factoring, right? Because the x-intercepts come from factors. But not every equation or polynomial that we come across might be factorable. So we're going to try to take a look at another technique here to help us figure out where some x-intercepts are located. So we're just going to start off with a simple example. Okay, this quadratic equation at the top, notice how it's a degree of 2. And we're going to kind of do a little investigation here. We're going to list all of the possible pairs of factors. I know if I asked you to factor this, we would be able to do that. What technique would you want to use, by the way, to factor that? Yeah? A times c. So we would do 3 times negative 6, which would give us negative 18. The b value is 17. Think of two numbers that multiply negative 18, add to 17. Yeah. Negative 18 and 1. All right. And from there, you would either do divide and slide if you're comfortable with that method, or grouping, right? So this one is factorable, okay? But when we get to some more complicated ones that aren't factorable, we're going to kind of have to list some possible factors, okay? Ones that may be able to go in evenly or may not. Now, if you think about factoring, okay, factoring is when you go from a standard form equation to the factored form, where you have those groups. Foiling or distributing, okay, multiplying, is when you go from the factors to the standard form. Okay, you go the other way. If you were to think about multiplying these two factors together through the FOIL process that we're familiar with, wouldn't the first terms have to multiply to get that term? And wouldn't the last terms multiply together to give you this one? If you did the outside and the inside terms multiplied together, they would eventually combine to give you the middle one. But the first terms always multiply to this first term in standard form, and the last terms always multiply together to give you that constant term on the end. So when we're going to list these possible factors, let's go ahead and think about the possible factors of this first term and this last term. So what are some factors of 3? Some numbers that you can multiply together to get 3. This one's kind of simple, yeah. 3 and 1, okay? So we know in terms of these factors that we're going to have some type of, maybe we'll write this here. This will be one of our possibilities. We need a 3x and a 1x multiplied together to give us a 3x squared. That's one possibility. What about the factors of 6? Specifically negative 6, sorry. What are some numbers you can multiply together to get negative 6? Yeah? 2 and 3, right? Okay, so these could be positive or negative values. Maybe we'll put plus or minuses in front of all of those. We should probably do the same thing here for 3, right? Well, maybe we'll just leave those as 3 and 1. So we have these possible factors that could be listed for these last terms. Maybe we have a 1 and a negative 6. Maybe we have a negative 2 and a positive 3. Just like we did all the combinations for positive, negative, 0, and imaginary in the last section, we're going to do all the combinations of these different factors. So if we take a look at the first terms that should be written in these factors, we know one of them has to be a 3x and the other one has to be a 1. in order to multiply here. But we have a few more combinations that could be listed for these last terms. Maybe we have a positive 1 and a negative 6. That would multiply to this constant term. However, another possibility would be, what if we had the same 3x and x, but instead of a positive 1 and a negative 6, we switched it. Negative 1, positive 6. Wouldn't those still multiply together to give you the last term? So we're going to try to go through all these other different combinations. Can we think of another possible combination of factors? Again, we know that we can factor this using one of our techniques, okay, but we're kind of guessing here. Maybe we forgot how to factor. Maybe this one's a little bit more difficult and we're not quite sure what to do. We're just listing some possibilities here. Can we think of another combination? Yeah. All right, so let's do negative 2 and a positive 3. Can we list another one? Yeah. Positive 2, negative 3. All right. There's still 4 more combos there. What if we kind of switch these numbers? Instead of the plus 1 being in the first factor, what if we put the plus 1 in the second factor? We haven't listed an x plus 1 factor yet, right? And then instead of the negative 6 that should be listed with that as well, we'll put that in the first factor. Okay, we haven't listed that combination yet. Let's maybe do the other ones. Maybe we have a positive 6 and then the minus 1. Maybe we have the minus 3 and the plus 2. Last one would be the, let's see, minus 2 and plus 3. Yeah? Did we already do that? Oh, it's up here. Sorry. You're right. Good catch. Okay, so these are all the possible factors just based of the concept or the idea that the first 2 terms have to multiply together to give you that first term in standard form, and the last 2 terms have to multiply together to give you that last term. Okay, possible factors. Let's say we weren't able to factor, we couldn't think of what to do. These are all the different possibilities. So if these are the possible factors, what are the possible roots? X-intercepts. Can we find them really quickly? What would the x-intercept be from 3x plus 1? Yeah. Negative 1/3. And then from the other related factor, yeah. We get positive 6. Okay, so if these are all the possible factors, let's list all the possible roots. I think you guys can do that pretty quickly. Oh wait, we have this one twice, don't we? Yeah. What was the what should this one be? It should be, should the minus 3 be there?
I put x plus 3 minus 3. It's the one above it.
X plus 3.
Sorry, 3x plus 3, x minus 3, my bad.
Oh, there you go. Okay. my mistake. So this would be -1 and then 2. Sorry, guys. There's a lot of combinations up there. I guess you could get lost, right? Okay, so we're going to kind of analyze this chart a little bit more in depth, and then we're going to eventually apply this to larger polynomials. This was a quadratic of power of 2. We know we can get larger than that. We can get cubic, we could get quartic, we could get quintic, okay, but this process really isn't going to change. So from the equation, what are all of the factors of the constant term? We already listed that. Our constant term was that -6 at the top. Okay, constant meaning no variable. So we'll go ahead and label that the constant term was -6. And we said all the possible factors were a plus or minus 1, a plus or minus 2, a plus or minus 3, and a plus or minus 6. The next block is asking us from the equation, what are all the factors of the leading coefficient term? Okay, that's kind of the first one listed out front in standard form. So the leading coefficient was 3. And we said those factors were 1 and 3. If you wanted to put the pluses and minuses in there, you could. Okay, might not be necessary in this case, but you could put them there too. Because technically -1 times -3 would give us a +3 as well. That is another case. So I want you to take a look at something here. We're analyzing all the factors of the constant term, and we're analyzing all the factors of the leading coefficient term. The ones in the middle are important, okay, because they are part of the equation, but they're not necessarily important for us to analyze to help us figure out where x-intercepts are located. So check this out. Now place each factor of the constant term over, okay, meaning some type of fraction, each factor of the leading coefficient. So we're going to take these possibilities from the constant divided by these possibilities of the leading coefficient. Let's go through the different combinations. What's a 1 divided by 1? That'd be a plus or minus 1, depending what your signs are. What if we did 1 divided by 3? That would be a 1/3, depending on what your signs are. Next, we can do 2 divided by 1, which would be 2, depending on what your signs are. Then we could do 2 divided by 3, which would be 2/3. Positive or negative, depending on what your signs are. Next, we could do 3 divided by 1, which would be 3. Another one could be 3 divided by 3, which is 1, but notice how we already listed that, right? So we're not going to list it again. We can continue to move on. We need a 6 divided by 1, which would be 6. And then a last possibility would be 6 divided by 3, which is 2, but we already listed that. Okay, so what do you notice about these values here? Good, Rebecca?
Some of them are zeros and possible factors.
Actually, all of them are. Okay. Did we list a positive? I can't really see it. I'll try to zoom out. Okay. Did we list a positive 1 and a negative 1 somewhere in here? At least once, right? Did we list a positive 1/3 and a negative 1/3 at least once? Somewhere in there? You see them right there? Did we list a positive or negative 2 somewhere? Yeah. Okay. So instead of trying to figure out all these factors, because let's face it, I kind of got lost in that process, right? Okay, so some of you might get lost too. And the larger these numbers are, okay, the larger that these numbers are from the equation, that just means the more factors you have, right? The more possibilities that you're going to write out. So it can get a little tricky in terms of looking at individual factors. But if we break it down a little bit more simply, instead of looking at whole factors, what if we just look at constant term versus leading coefficient? We're still going to get the same possible roots in the end. We're just not analyzing factors. Okay, we're analyzing factors of the numbers, not factors in terms of quantities. Okay, so this is what's called the rational root theorem. That's what we're kind of going to formally define on the next page just in a little bit. But we're going to take a look at another example. Notice how this one is cubic. Okay, so a higher power might be a little bit more difficult. We're going to graph the function on the graphing calculator, and we're going to try to identify the roots. So that's why I wanted you to get one today. Let's go ahead and turn it on. And we'll type in the equation. Let's go ahead and we'll set the window. Maybe we'll do 5s in every direction. We can always go back and change it if we need to. And we'll go ahead and hit graph. Alright, so on your notes, I want you to draw an accurate graph. Okay, we're specifically looking for x-intercepts, so we might want to be especially accurate or pay attention to those pretty closely. So if we were to draw a graph, maybe we'll throw in some tick marks on the x-axis. If we were to label some of these x-intercepts, it looks like we have one of them going exactly through -3. So we'll put a little dot there. But notice how the other ones we have there are not going through a nice tick mark, meaning they're not a nice whole number. They're going to be some type of fraction or decimal value. So we can say that we're kind of close to -1 on the left-hand side and what looks like about a half, but again, we're not too sure on the right-hand side. So we have one over here and one over there. And following the shape of the graph, we'll go ahead and draw a rough picture. Bless you. Alright, so let's go ahead and label what these roots or x-intercepts kind of look like, what they should be. If you hit the trace button, your little cursor should pop up somewhere. You may have to use the arrow buttons if you can't see it initially. Okay, but what we're going to do is we're going to try to get that cursor as close as we can to that x-intercept. If you notice on mine, I can't really get to it really close, like exactly. But if I keep going back and forth between the x-intercept, notice how my x value keeps bouncing back and forth between 0.42 and 0.53. So can we take a guess as to where the x-intercept might be if you keep bouncing back and forth? Do you think 0.5 makes sense, perhaps? Okay, so we'll say one of the roots looks like it should be about a half. I'll use little squiggle marks. Let's do the same thing for the other ones. We're going to get the cursor as close as we can. Alright, I can't really get it exactly, but it looks like it's really close to -0.63. And then if I go above it, it's -0.74. So something between those values. Maybe we'll say -0.69. These are just guesses. Now the last one was pretty obvious, right? Do we see how it strikes through exactly on that tick mark of -3? Again, you might not be able to get exactly on it, but if you're bouncing between -2.97 and -3. What is that? Oh, you're probably a -3 in there. So we'll say -3 as an exact one. Okay, so what's going on with this graph? The problem with this graph is that one of the roots is -3. Okay, we can clearly see that, but the other two are not nice whole numbers. Notice how we had to estimate what they were roughly. So what we're going to do is use this rational root theorem. Do we know what the word rational means? Have we heard that before? Okay, rational means fraction. Maybe you can see the word ratio in the word rational. Ratio just means some type of comparison, and you can represent a comparison through a fraction. So what we're going to do is we're going to list all of the possible fractional roots, kind of like what we did on the front page. So the rational root theorem tells us, by definition, that the complete list of rational roots is found by dividing the factors of the constant term by the factors of the leading coefficient term. Okay, basically what we noticed on the front page. If you were to take all the factors of the last term divided by all the factors of the first term, you would get a complete list of all of the possible ones. Maybe we can use a calculator to figure out which ones they are exactly. Okay, but at least we can develop a list of all the possible ones. Kind of like what we did in the last section. We developed a list of all the combinations of how many show up on the right, the left, the origin, and our imaginary, and then we used a calculator to confirm. Okay, this is going to be a very kind of similar process. So let's apply this rational root theorem to this problem or this graph that we were analyzing at the top. Okay. Can we identify the constant term versus the leading coefficient term? The constant term would be, yeah? -6. Okay, so we need factors of -6 divided by factors of the leading coefficient term. What's the leading coefficient? Leading number up front? Yeah. +6. Okay. So let's go ahead and think about some factors that you can multiply together to get a -6. You could have a ±1 times a ±6, depending on what the signs would be. You could have +1, -6, -1, +6. All those would multiply together to give you -6. Some other factors that can get you to a -6? Yeah? A 2 and a 3. Good. All right. What about numbers that can multiply together to get you a +6 for that leading coefficient? You could have a +1 times a +6, but you could also have a -1 times a -6, right? Those would give you a +6 in the end as well. Looks like we would also have the same ±2 and ±3 as some options. Okay, so we're going to take all the possible factors of the constant divided by all the factors of the leading coefficient, and we're going to list all of the possible fractions. Okay, that's why it's called the rational root theorem. These are going to be fractions. They may simplify to whole numbers, but they are fractions nonetheless. So let's go through all these possibilities. We could have a 1 divided by 1, which would be a plus or minus 1 depending on the signs. We could have a 1 divided by a 2. We could have a 1 divided by a 3. We could have a 1 divided by a 6. Another possibility, if we move on to the next factor of the top, we could have a 2 divided by a 1. Next would be 2 divided by 2, but that reduces to 1, which we already listed, so we're not going to worry about listing it again. If we move on, we would have a 2 divided by a 3. Next, we would have a 2 divided by a 6, but that reduces to 1/3, which we already listed, so you don't have to worry about it. If we keep going, we have a 3 divided by a 1, a 3 divided by a 2, 3 divided by a 3, but that's 1. And lastly, a 3 divided by a 6, but that's a 1/2, and we already did that one too. Moving on to the last factor of the top, we have a 6 divided by a 1, 6 divided by 2, but that's 3, we already have that. 6 divided by 3, that's a 2, we already have that. And a 6 divided by a 6 is a 1, we already have that. So it looks like those are all the possibilities. Alright, now clearly the graph doesn't have all of these as x-intercepts because we only identified 3 of them. Okay, these are just a list of the possible ones. So from this list, let's eliminate those that don't appear to be the right ones based off the graph. Okay, so if we take a look at the graph from the top, I have to zoom out again a little further. Alright, so our first option here, we had a plus or minus 1. Clearly we didn't label either of those on the graph, so we can cross that one out. We did mention though how perhaps it looks like we have one at a half, so maybe we'll list x equals a half as a possibility. We didn't list any of them for 1/3, so we can cross that one off. We didn't list any for a 1/6, either positive or negative, so we can cross that one off. We didn't list any of them for 2. What is 2/3 as a decimal? Do we know that off the top of our heads? Yeah? Say it again?
Like 1.5.
That's 3 over 2. Okay, that would be this one. But what's 2 over 3? Yeah? 0.66666 repeating, okay? And based off our calculator, didn't we say 0.69 was roughly one of the options, right? That's pretty darn close to 0.66 or 0.66666. So maybe we'll list a negative 2/3 as the other option. We also listed negative 3 at the top. That one was pretty obvious from the graph because it went through that tick mark. Maddie just told us that 3/2 is the same as 1.5. We didn't list that at the top, so we'll cross that one off. And we clearly don't have a 6 listed. Okay, so that one's gone. So notice how the x-intercepts we found based off the graph are a part of the possible options. Okay, they should be. So how do you think we can confirm or verify that these are actually roots? What have we talked about in this unit that we can use to verify if something is a root, aka an x-intercept, aka a factor? Yeah?
You said that if we divide it and you get a remainder of 0, you know it's a root.
We know it should go in evenly, right? Okay, so we're going to test these. Alright, so if we are correct, based off of our calculator and this rational root theorem, these should result in a remainder of 0. So let's go ahead and try it. Maybe we'll do the 1/2 factor first. Or do you want to do the -3? Do we like a whole number first? That one's kind of the simple one because we can clearly see that that was an x-intercept based off the graph. Our synthetic division setup would be 6, 19, 1, and -6. Do we need a refresher on synthetic division, or are we good to go? I'll take the silence as we're good. Remainder of 0, right? So we know that -3 is an x-intercept. Now maybe we'll test 1/2. Now here's what you could do. You could use the same synthetic division coefficients, the 6, the 19, the 1, or the -6. Or we also discussed how you could check the quotient values, right? Because shouldn't the quotient be a factor as well? That should go in evenly. So maybe we'll use the 6, the 1, and the -2. It doesn't matter, okay, but maybe working with 3 numbers, it might be a little quicker for us instead of the 4 from the other one. Notice how we get a remainder of 0. So we were correct with our guess from the calculator that the 1/2 was the correct x-intercept. And if we try the last one, we'll do -2/3. Again, you can use the 4 original coefficients, or you could take the quotient values from the previous division. In this case, we'd only have 2 numbers to work with, which is maybe a little easier. Let's see, 6 times -2/3 would be -4. And notice how we get 0 there too. All right, so based off the graph, we were able to get a rough idea where the x-intercepts were located. Using the rational root theorem, okay, we could assume that our guesses were most likely correct because they were listed as possibilities. And then we're going to confirm or check it using our synthetic division. Okay, we want to get those remainders of 0. Okay, how are we doing with listing these possible factors? Can we list all those based off the division? Are we okay with all those combinations? There might be a lot of them, okay, but we're going to check them just to make sure in the end. Let's try another one, okay? We have 3 examples to go over. That's basically all we're doing here. Okay, we're going to list all the possible x-intercepts and then check them on a graph and confirm them using synthetic division. Okay, so let's, maybe with this one, we'll start off with the rational root theorem. Let's make our list of possibilities. We need the factors of the constant term divided by the factors of the leading coefficient. All right, so our constant term is 10. Our leading coefficient is 6. Can we identify some factors of 10? Good, Rebecca? 1, 2, 5, 10. Okay, don't forget the plus or minuses because depending on the signs, those would need to be taken into consideration. Factors of 6, I think we've already done this in previous ones. We had 1, 2, 3, and 6. All right, so based off those factors, we're going to divide all the possibilities. Remember, if your fraction simplifies or reduces to a possibility you've already listed, you don't have to write it again. I think we should have 12. 1, 2, 3. Yeah, looks like you should have 12 possible x-intercepts with the pluses or minuses. Alright, so if these are all the possible ones, we're going to go ahead and graph it to see which ones we should pay more close attention to. Okay, which ones seem to be the actual x-intercepts instead of just possible x-intercepts. Alright, so on your calculator we can clear out the last equation and we'll type in this new one. Go ahead and hit graph. We're going to pay close attention to the x-axis. Maybe draw in some tick marks on your paper. And if we use our cursor to get kind of close to where we think they are, let's see, it looks like we have one exactly at 2. Go straight through that tick mark. We have another one. Ooh, there we go. Really close to 0.319. Okay, so maybe we'll make a list over here. X equals 2. Roughly we'll say 0.4 or 0.3, somewhere in there. Maybe 3.3, 3.2, something like that. And we have another one on the left-hand side. Did I go past it? Oh. So I bounce between negative 2.4 and negative 2.55. So probably negative 2.5, somewhere in the middle. Can we get those numbers on our calculator? Calculator work going okay? Alright, so here's a little rough sketch if you wanted to draw one. Alright, so let's go ahead and based off these ones that we kind of identified off the graph, which of these are showing up in our possible list? Okay, we didn't list any that were plus or minus 1, or even close to those. We didn't list any that were close to plus or minus a half. What's 1/3 as a decimal? Yeah? 0.3 repeating, 0.33333. And notice how this one was pretty close, right? 0.32. So maybe we'll say that we need a positive 1/3 based off of this one that we identified from the calculator. We didn't identify anything close to 1/6. We did identify a 2, right? Exactly. 2/3 as a decimal is 0.666. We didn't list anything like that. We didn't list anything that was exactly 5. What about 5/2 as a decimal? Yeah, that's 2.5, and we listed something pretty close to that. It happens to be negative, so we would need a negative 5/2. And it looks like those are the three options that we had based off the graph. So all the other ones, even though they were possibilities, they are not actual ones. Okay, so if these are the ones based off the possibilities, okay, from the graph that we analyzed, let's go ahead and confirm, okay, verify that these are actually the ones based off of the equation. So to verify, we're going to go ahead and use our synthetic division. Maybe we'll start off with 2. Okay, nice easy whole number to work with. And we'll take the coefficients from the polynomial. So it looks like 2 is a root. It goes in evenly. Maybe we'll try 1/3 next, using the 6, the 13, and the -5. We get 0 there as well for our remainder. And our last one is the 5/2, or -5/2. Kind of running out of room. But we get 0 there as well. Alright, so based off the rational root theorem, we listed all of those different possibilities. We then use the calculator to kind of narrow it down a little bit, okay, of the possibilities, which ones make sense. And based off of those ones that we narrowed down, we then verify, okay, to confirm that they are actually the x-intercepts of this graph. So our roots are the 1/3, the 2, and the -5/2. We doing okay so far? Alright, we'll check out the last 2 tomorrow. Okay, probably a good place to end. That way we have a good refresher to work with tomorrow. Okay?